Also, very much Robert for inviting me. It's been great to get out of the US during this period and learn about a lot of interesting things. Today I'll be talking about some efforts we've done to NISC computational phases of matter, which is a string of words that hopefully by the end of this presentation we'll both mutually understand a little bit better. This is work done in collaboration with Arnab, Dimitro, and Robert. Arnab and Robert, who are both now at Hanover. So this presentation is based largely on these three works, the top two kind of forming the theoretical basis for what we'll be discussing. And I wouldn't, but if you so choose, you're also free to look at my master's thesis for some of the details and an archive posting that I really should not guarantee by this Friday. So now we can get into some of the motivating questions, which I think kind of both sit nicely towards the aims of this workshop, like looking at quantum information processing in the near term. We've seen a lot of different perspectives on how to answer these two questions, and here I'm going to provide yet one more flavor. So the first being, how do we characterize quantum computational speedup or advantage? And the second being, with these noisy small devices we have available, what are interesting things we can do? So towards this first question, I'm going to propose this framework of measurement-based quantum computing as potentially giving us insights towards these kind of questions. And towards the second question, yesterday I think there was this big debate where the pessimists won towards what is, the use of near-term quantum devices for realistic advantage. I'm going to stay agnostic because I'm not going to claim any sort of advantage towards anything we're doing whatsoever, and this is just kind of using these devices as fun explorations of phenomenology that we might know. So although this idea was conceived in Munich, and therefore I'm going to expect all of you to be experts already, nevertheless, I'm going to just review what I mean when I say measurement-based quantum computation. So on the left, we have a very simple circuit in our familiar circuit model of computation. We start with our unentangled register of qubits. We do some set of unitary gates, probably picked out of some universal gate set. And at the very end, we do this measurement for the last time step just to read out the information. Maybe we repeat this some number of times to collect statistics. The measurement-based formalism kind of turns all this on its head. So instead of starting with this unentangled register of qubits, I instead am provided a resource state that's already entangled. In some sense, the entanglement comes like pre-packaged in this canvas that I've already given you. And on this state, what I'm going to do is a sequence of only single qubit adaptive measurements. So no more entanglement than was already provided in this state is ever going to be generated. And through this sequence of adaptive measurements, I can actually carry out any universal quantum computation. It's equally powerful as the circuit model in that sense. But it nevertheless is kind of surprising because it kind of maybe defies your intuition about, do you need to generate entanglement? Well, no, not actually on the fly. You can kind of be given to it all right at the start. And therefore, kind of thinking about what sort of resource states are capable of being this measurement-based canvas might give us intuitions into where the heart of quantum advantage is lying. In this talk, I'm going to focus on resource states in one dimension. Full disclosure, this already means that we're not even thinking about universal MBQCs in the sense that you can kind of see from this diagram, we're only being able to simulate one logical qubit in simulated time. But kind of 1D being the simpler case, we really fairly well understand on the theory side what these resource states look like. And also, this is probably the most amenable to actually realizing these kinds of effects on near-term processors. So I'm going to define what I mean when I say computational power of a resource state. And when I say that, I mean that by doing these adaptive single qubit measurements, I can do arbitrary single qubit unitaries on my encoded single qubit with high fidelity. So this is kind of a logically high fidelity. I think this will make a little bit more sense in a couple slides when I flash a channel that precisely characterizes what I mean. So stay tuned for that. And just to give you two examples, although really it's more like one example and one non-example. On the left side, we have the cluster state. This is kind of the canonical measurement-based resource. It's the ground state of this stabilizer Hamiltonian and is where this kind of entire formalism was developed originally. And on the right side, you have a product state, something that's completely non-entangled. So if I told you that you'd be able to do quantum computation by doing local measurements on this, you'd say I was insane. And you'd be right, it's completely useless. But now you can ask, well, what happens if I take these two Hamiltonians and I interpolate between them? What does kind of the computational power landscape of this guy look like? And perhaps surprisingly, it turns out that it splits up into two distinct phases. One, where you have kind of uniform computational power, so all the states in that aspect of the phase diagram are as powerful as the cluster state, and this phase where essentially all states in that phase are as computationally useless as the product state. And this is kind of one specific example of this more general result of computational power being uniform in SPT or symmetry-protected topological phases, and to kind of flash the more quantum information theoretic definition of what that means. Two states are in distinct SPT phases if there's no, if I can't connect them via symmetric finite depth local unitary. And if anyone here has ever thought about topological order, you might notice that this condition is very similar, just you kind of erase the symmetric bit. But enforcing that these finite depth local unitaries, or if you like local quantum circuits, kind of preserve the symmetry is what allows this kind of extra aspect of symmetry protected phases. So, you know, a priori, it's a little confusing that everything on this left side of the phase diagram is as powerful as the cluster state, and you'd be right to doubt me. And it does actually turns out, the moment that you step away from this kind of one point of the cluster state, you do actually get logical decoherence when you try to do MBQC. And here's this channel that I promised. So if you're working with the cluster state, you have this perfect rotation, but that becomes, away from this cluster state, this probabilistic channel. So now, as I do my local measurements to evolve the logically encoded information, I actually get this kind of probabilistic combination of two unitaries. The cluster state is the case where nu, this computational order being 1, so I recover this perfect rotation. But as I go away from this cluster state, this computational order parameter decays. So I am no longer able to do these operations with perfect fidelity anymore. One of the things that it was shown in that first reference that I flashed on that title slide is it turns out that this computational order parameter is equivalent to another property of these states, namely their string order. So you might be familiar with order parameters and thinking about conventional phases of matter, and this is kind of the equivalent thing for SPT phases, where I have this string of polys that essentially extends from one end of the system and here to the site where I do my measurement. And it turns out that this quantity is exactly identified with the computational order of the state. So if you weren't too sleepy from lunch and paying attention, then you might be like, okay, sounds like I'm saying two different things on this side and the last one. On the last one, I said, I have all these states, they're uniformly powerful. Here I'm saying, actually, they're not uniformly powerful because there's decoherence. What's going on? And it turns out that we have techniques to precisely manage that decoherence, and that's what allows me to make this statement about a computationally universal phase. So in particular, if I have this, laser pointer time. If I have this single rotation, I can split it up into smaller sub-rotations, and in particular, assuming that I have an infinitely long chain, I'm going to split them up such that this rotation splitting is a lot larger than the correlation length of this system. So that allows me to treat these kind of small rotations independently. Then, as long as this rotation angle is small enough, I can Taylor expand that probabilistic channel, where I find that this deviation from unitarity actually goes as quadratic in this rotation angle. So if we combine these two ingredients, we see that this total error is just going to be m splittings times the error for a single rotation, which we established as quadratic. Therefore, the total error coming in as this beta squared over m, which means as I increase the splitting, I can arbitrarily approximate any rotation unitary to my desired fidelity for whatever amount of error that I want. And this is kind of precisely the reason why I can say I have this computational phase of matter. It's because, you know, if I have truly like an infinite line to work with, I can split my rotations as far as possible. I can also split this rotation as arbitrarily small as possible. And therefore, anything with a non-zero string order parameter is going to give me something that can perform, maybe at the expense of more resource, a rotation as good as the cluster state. Are there any questions so far? All right. In the finite case, there's kind of an additional subtlety where there's these two different effects. So on one hand, I mentioned that splitting the rotation is beneficial for reducing the logical decoherence. On the other hand, I mentioned that spacing out these rotations is beneficial because I can kind of treat these as independent operations, which I then compose. So you might ask, okay, if I only give you 20 qubits to work with instead of infinity number, what exactly would be the optimal thing to do? Do I split more or do I space out more? And the second reference indeed says that splitting is the winning team here. So the most error-reducing protocol you can do is to split the rotation as finely as possible, which kind of tells you in finite systems, just chop up your rotations as much as you possibly can. So this sets the theory stage for the three phenomenological effects we want to explore. The first is this notion that computational order and string order coincide. The second is this kind of fundamental unit of decoherence management where I split up this logical rotation. And the third is this kind of counterintuitive regime where I split up the rotations as finely as possible. And this gives me something that's optimal in terms of the total error. But before we can realize that, we need to think, okay, well, what states exactly are we going to try to realize and see these effects in? And to this end, we recall our little interpolation Hamiltonian that takes us between the cluster state and the product state. We propose this variational ansatz for approximating the ground states of this sky, which you can, one way to understand it is like a local imaginary time evolution via a product state X Hamiltonian on top of the cluster state. And we're motivated by this just because it shares the symmetry of the cluster state. So in some sense, it should be in the same SPD phase. And also, when you do perturbation theory, you find that this is kind of the correct form to second order, what you find of your approximate ground states. Then, as kind of we've seen in VQE before, for a given value of alpha, ground state that we want to approximate, we look at this expectation value of the energy, minimize over theta, and that's going to give us our approximation for the desired ground state. There's a little bit of subtlety in actually how we compute these, coming from the fact that the sky is not unitary. If you are curious about that, feel free to ask me at the end. So here, big plot, but we'll break it down. We actually see the result of measuring these independent energy terms in the Hamiltonian, the solid lines being the theory curves and the little dots being the actual experimental data we measure from IBM's superconducting processor. We see that we have pretty good agreement between the two, which is perhaps not surprising because a lot of these can be measured in very small circuits. And to give you a little more context about what's going on, at this 0 point of the variational parameter, we see that these cluster state stabilizers have expectation value 1. The product, this local magnetic field has expectation value 0. So at this point, I am actually just realizing the cluster state. The T theta transformation is doing nothing there, so that's perhaps to be expected. Conversely, at this theta equals pi over 4 point, I have that the cluster stabilizers are 0, while this local magnetic field approaches 1. Yeah?
One very, very silly question.
Yes.
Do you have any intuition why in the blue curve the experimental points always overshoot the theoretical line as in the red one, whereas in the green case it always undershoots?
Yes, that's a good question. At least, let's see. In terms of the complexity of performing these circuits, both the blue and the red turn out to be to compile to a single qubit circuit versus the green curve compiles to a single qubit circuit, which then conditions another gate in another small circuit. So I think it's perhaps not surprising that the blue and the red have the same behavior because it's kind of the same circuit modulo starting state, and the green one has a distinct behavior, but I don't have a great intuition as to why there's a significant over or underestimation. Yeah, so the groupings make sense to me. Which directions those flow in are, I think, is a little bit lost, yeah.
The match is anyway very nice, so this is no criticism.
Right. There you go. Yes.
So this is all in 1D, right?
This is all in 1D, that's right.
So isn't it dangerous to use a perturbation argument in 1D because if you have a finite density of errors somehow, it would mean that in the limit of the chain going to infinity, the string order vanishes. In 2D, there, you know, you can do percolation and all, but in 1D, could it be that you have to be careful what you limit there? No, like how do you? So I'm a bit confused about that.
I see, I see. So I guess, sorry, just processing the question. The objection is that like in the thermodynamic limit, I probably wouldn't expect that this perturbation theory like argument gives me actually like a valid
Let's say
state.
like the actual state
Yeah.
is off to the real state.
Yeah.
But I would expect it to be kind of like a local density of errors. Say if you actually use that chain to transport quantum information, you have an effective like small decoherence in every teleportation step. Whenever, yeah? But then as the chain becomes longer, no information that you put into the left will ever make it out to the right. Do you see what I mean? So I think like, can you actually conclude that the string order is there in 1D from an argument that might have a finite density of errors?
I see.
I mean, it might well work. I'm just
Yeah.
I would also be much less worried in 2 dimensions.
Right,
One,
right.
I don't know.
Yeah, I think, I mean, what I can say in one dimension is that, like, you, in fact, for any value of theta, you actually are in the cluster SPT phase, even in the
You know
thermodynamic.
that from different arguments.
Yes, that's right.
Oh, okay,
yeah. Though this is something that, like, we thought about and realized after the fact, and only actually at like this one point where it becomes a projector are you actually kind of immediately cutting to the product phase. Yeah, but
Okay.
no, I
There's a different way of ascertaining that the answers actually make sense.
yes, that's right.
Got it.
Though,
Thank you.
yeah, it certainly is not. Yeah, there's also, I guess, doubts because you're making the ansatz around the cluster state as well. Like, how far does it even make sense to trust this? Yeah, so there's also other considerations in that sense. Yeah. Right, very good questions. So after we calculate these three curves, what we can do is essentially kind of add them up as the Hamiltonian dictates, and for a given value of alpha, optimize and pick the optimal variational parameter theta. What then gives us is, well, shown here for red is this n equals 5. You have this little bit of steppiness coming in from the fact that, of course, these experimental curves you're optimizing over aren't quite smooth. But shape of the curve seems pretty believable to me. Also, for comparison, I have done like the n equals infinity calculation where it can kind of be done explicitly. And I guess a little bit of a cute feature is that you still recover a sort of phase transition in the system, even though it's at the wrong location. So yeah, little curious feature of the ansatz, even though it's quite simple. Right, so now that we know what states we're working with, we can get into kind of testing our phenomenology. So our first test of this equivalence of computational string order is going to be done in this very small 5-qubit setting. So for the string order, all we need to do is just prepare the state and then measure this clustered state stabilizer. Extends from this rotation site to the end of the chain. To measure the computational order, I do like a very, very small MBQC scheme just on 5 qubits, where start with a plus state, do a single rotation on this third site, and do the state tomography for the logically encoded qubit. And based on my expression for this channel I had earlier, I know that the expectation value of the logically encoded x is just goes as cosine beta, for y goes as nu sine beta. So taking this ratio, I can basically have this effective line of tan beta versus this ratio with nu as the computational order parameter. So this gives me two kind of distinct ways to measure these, which we can then come back and compare. So it's also worth noting that we actually kind of get this guy for free from doing this variational process, because this is exactly the stabilizer that we already measured there. So this is now the results of plotting that ratio against tan beta. So if you believe what I say, then we expect these to look like lines where the slope is governed by this computational order parameter. So indeed, we can take these curves, which at least I would believe look pretty linear, and fit them. And then if we compare against the independent measurement of the string order parameter here, we can see that, okay, again, there's a little bit of deviation, but at least I can reasonably believe here that those two measures of the computational and order and the string order coincide. Admittedly for this very small system, but as a proof of principle, I would hope that you are also somewhat convinced. So great, there's experiment 1 on the books. Now let's go to experiment 2. So here we want to investigate this nature of splitting, decreasing this logical decoherence, and in particular this 1 over m effect, where if I split m times, does the decoherence go down as 1 over m? So to do that, I essentially just compare 3 protocols where I split 0 times, or split into 2, only 1, or 3. And then I can measure the loss of purity of the encoded information just by doing this state tomography, much like this last case. And if I find that this loss in purity scales like 1 over m, then, well, there's our demonstration. So indeed here what we have is for kind of the limit of small rotation angles, we expect this error to scale quadratically. And that's what we see. We also compare to just a very, very simple noisy simulation with a like 2-qubit depolarizing noise channel. Completely unrealistic in terms of what's going on in the machine, but still kind of captures the features of the decoherence quite well. Also maybe worth commenting, these being the theory curves, we see that even at 0 rotation angle, you already have loss in purity. And that's, of course, coming from the fact that we're doing this on a fundamentally physically noisy device. So if you indeed fit these curves and kind of plot, okay, what does the behavior look like as 1 over m, you get 3 points, which you can then linearly fit. You might be like, okay, come on now, 3 points. To that, I'd say, okay, at least it's not 2. And also, even at already doing 3, you might try to think, okay, if you did 4, probably these are no longer going to be indistinguishable. So again, kind of proof of principle. I think you're completely free to nitpick that 3 points in a line isn't a lot, but nevertheless kind of seems to follow the qualitative scaling behavior that the theory predicts. Finally, we go to this experiment 3, which is in this regime where you do actually have correlations measuring what the most optimal strategy for reducing decoherence is. And for this, I kind of originally gave this VQE ansatz, but this guy actually has no length scale because it's just a local deformation of the cluster state. So I wouldn't be able to expect to probe the effects of correlations on this. So we instead kind of consider like the next most correlated step up that still retains the symmetry. So these kind of next nearest neighbor XX rotations on top of the cluster state. And on this guy, what we're going to compare is these 3 protocols. So 2 close rotations, 2 far rotations, and kind of maximally split rotations. So if what we kind of understand about decoherence is correct, then we say, okay, well, these 2 rotations are correlated, so I probably expect that this performs the worse. Here, now these rotations are at least independent, so I expect that 2 performs better than 1. And because here I'm now splitting as much as possible, our theorem that, okay, kind of splitting is the most dominant factor should tell me that this is better than this and this. And when we actually look at the results, we seem to, again, qualitatively, you get the correct ordering of the curves, where 2 close rotations followed by 2 far rotations followed by maximal splitting of rotations. I do have like a personal nitpick with this curve that it isn't actually consistent at 0 where nothing should be happening. So this is still something we're working on and thinking about redoing. So yeah, I would say personally the jury's still out on this one. All right, so what do we see? So I felt personally, I don't know about you, felt pretty good about computational order equals string order. I felt pretty good about the 1 over m, even though we only had 3 points. I don't know how I feel about this last guy. Maybe as outlook, I mean, our circuits are like on 11 qubits and like are maybe depth 6 at most for 2 qubit gates, yet we see very noisy results. So maybe just as like a cautionary tale of even doing seemingly very simple things, if your problem doesn't have the correct structure, still can be very difficult to detect and measure things. Anyways, that's the end of my talk. Thank you very much for listening.
Thanks very much. Questions? Oh, I thought there was a hand.
So very nice work, but concerning this about the experimental data and so on. So I mean, of course, if you don't use any error mitigation techniques, which you didn't use now, as far as I understood, right?
We used like measurement error mitigation and like polytwirling.
As a like you use this T-Rex type of thing, right?
Yes.
basically. But did you also use after that measurement error mitigation? So to take out like you inverted the errors there, like
let's see. Okay,
like this
so
confusion matrix, inverted that.
right. So on like a individual measurement record level, we did do this kind of inversion of the
Yeah.
matrix.
Okay.
Yeah.
Okay. So this is like the lowest level of
Yes.
error mitigation. You cannot expect much more. I mean,
Yeah.
you go to circuit sizes which people are doing now is like 100 qubits,
Yes.
depth 100. You need these error mitigation methods, and then the biggest sizes where you can use this, there are these arguments for how many samples you have to do that.
And
then
they're exponent.
it becomes like 300 times 300,
Right.
or well, very optimistic 1,000, 100,000, but more like 300 times 300. So that will be the limit. I think that's yeah.
Yeah, there was also, I mean, I think there's this like zero noise extrapolation technique, which we didn't use particularly because we tried, and then I was like, okay, we effectively choose the fitting function that appears to give us the result we want the most, and this seemed a little bit ungenuine in some sense. Like it's not, yeah, we wanted to just use like bias-free type, yeah. But no, it's a good point, yeah. Thank you.
Great. More questions? So you already had a bunch of great questions during the talk.
Yes.
David thought about this question as a follow-up.
Yeah, I came here so you didn't have to walk back. So, of course, the question is in terms of computational phases, can you do this in 2D, you know, where everything is much more computationally relevant?
Yes, that's right, yeah.
Any thoughts on how to go to 2D?
I would say I'm pretty pessimistic about like any experimental foray into 2D recently. Yeah, considering that 1D was already like a nightmare for me.
But not the experimental stuff. I mean, you have some, like the perturbation arguments and stuff like that.
Right. Yeah, I guess for 2D, like on the theory side, what would be relevant is, okay, there's not like a complete classification as there is in 1D. I think there's been some work or some ideas that Arnav and co have been thinking about of like, okay, you have this kind of string order way of tracking computational order, which is like a little bit more robust maybe. And is there kind of a natural extension of this to 2D? Seems like a little bit subtle. I think there's also there's been more work in 2D showing that like, okay, even things that are not SPTs can have computational order. So I want to like long-range entangled states. So I think the setting there's still quite not well understood. Yeah. So yeah, I would agree that there's a lot more work to be done. Yes.
One last question. Anyone? Well, if not, let's thank you again. And next up's David.